For the next several weeks, we'll be talking about compounds that contain conjugated pi bonds. So I thought a logical first step in this video would be to talk about what's the definition of conjugated pi bonds? How do they look from a molecular orbital theory perspective? How does that affect their energies? And then talk about some reactions that conjugated pi bonds undergo that are a little bit different than isolated pi bonds. So to begin, we'll look at two different alkenes, right? We have this one, which is conjugated. We have these two alkenes are isolated. These two alkenes are conjugated. So what does it mean to be a conjugated alkene? Well, it just means that you have a carbon-carbon double bond and another carbon-carbon double bond, and they're only separated by a single bond, right? These two carbon-carbon double bonds are separated by two single bonds, or if you're separated by two or more single bonds, you're not conjugated. But the real definition of conjugation, the way that you want to think about conjugation, is thinking about this in terms of molecular orbital theory and thinking about this in terms of what the pi bonds look like, right? Remember, anytime that you have a pi bond, you have two p orbitals that are next to each other, right? But then you have another set of p orbitals here that are next to each other. So one might hopefully expect that these electrons can kind of diffuse throughout all the p orbitals. And as we've said with acid-base chemistry, the more that we can spread out electrons, the more stable that these things are going to be. So what we're going to find is that conjugated pi bonds are more stable than isolated pi bonds, just because we're spreading out the electrons more. And how do we measure stability? Especially stability of alkenes, we can measure it through hydrogenation, right? So if we take two equivalents, or 2 moles, let's say, of one butene, and we hydrogenate it to make butane, we get 254 kilojoules of energy out, right? But then if we hydrogenate 1,3-dibutene, then we get only 239 kilojoules of energy out. So the difference here, this 15 kilojoules of energy difference, is stability associated with conjugation. That makes sense, right? This is lower in energy, so when we hydrogenate it to give the same compound, it releases less energy because it's more stable. The more stable you are, the less energy that you release. The less stable you are, or the higher energy you are, the more energy that you release to give the same product, right? So we know that conjugated double bonds are stable because they release less energy when we hydrogenate them. So they were lower in energy to begin with. So to really understand this, I just want to quickly recap. Remember that to make bonds, what we do is we take atomic orbitals and we overlap them. And when you overlap two atomic orbitals, you can create molecular orbitals. And what you must remember is that the combination of two atomic orbitals creates two new molecular orbitals, which I'll show you on the next slide, right? So remember, and let's say for a very simple example like H2, right? Hydrogen has an s orbital with one electron in it, and the other hydrogen atom has an s orbital with one electron in it. And those can combine to make a bond. And when those two orbitals combine, they make two new orbitals. They make a bonding molecular orbital and an anti-bonding molecular orbital. We're lucky here because we have two electrons, so they both funnel down into the more stable bonding molecular orbital. And there's no electrons in the anti-bonding molecular orbital. So remember also, when we have a pi bond, we have two p orbitals. Each one of those has one electron, so they form a pi bond and an anti-bonding pi bond. But only the pi bond gets the two electrons. So again, here we have a p orbital, right, with one electron in it, and another p orbital with one electron in it. And when they combine, they form this pi bond that contains two electrons. They also form a pi star, or a pi anti-bonding molecular orbital, but notice that this doesn't possess any electrons in it. What we'll find, though, is that if you have 4 pi bonds, they can combine to make 4 molecular orbitals. So you can get 4, and actually let me go back one. Notice that if you had a p orbital. We said this is red and this is blue. We have another p orbital that's this one's red and this one's blue. They can overlap, so those two phases are in phase with one another. Another way to depict this is plus minus and plus minus. So the pluses are in phase with one another, the minuses are in phase with one another. That's a bonding. If they're out of phase, that's an anti-bonding arrangement where they're repelling one another. So again, we can have 4 p orbitals that are all in phase with one another. That's going to be even more stable than a single pi bond because now we're spreading electrons out over a longer distance. So this is our first bonding orbital. Then we also get another bonding orbital. Remember, too, that as we increase in energy, we increase the number of nodes, just like in atomic orbitals. But we have 4 p orbitals, 1, 2, 3, 4, and each one has a single electron in it. So we take those 4 p orbitals, we combine them to make 4 molecular orbitals, and we fill them according to the Aufbau principle, where we do 2 electrons that are spin paired. So we put 2 electrons in the lowest energy orbital, we put 2 electrons in the next lowest energy orbital, and here's the line between bonding and anti-bonding. So if we just had 2 pi bonds, or 2 p orbitals to make 1 pi bond, the energies would be something like this. So the net energy of these 2 or 4 p orbitals is lower in energy than we would if we just had 2 p orbitals, and that is called conjugation. Okay, so the last thing we're going to talk about in this video is reactions that conjugated double bonds undergo that are a little bit different than isolated double bonds. So we know that if you have a double bond, that it can undergo hydrobromination, where the hydrogen goes to the less substituted carbon and the bromine goes to the more substituted carbon. What's strange about this particular reaction now is that we can also get this product. So we have different names for these. Since we can number these carbons 1, 2, 3, 4, we call this the 1,2 adduct or the 1,2 product because the hydrogen and the bromine added to carbons 1 and 2. We call this the 1,4 product because the hydrogen added to carbon 1 and the bromine added to carbon 4. So what you're asking yourself probably is, where did the 1,4 addition product come from? And that's what I'll show you in the next slide. Okay, so let's say we start with this alkene. Remember, the mechanism for any addition to an alkene using hydrogen bromide, or HBr, is that we protonate the double bond, and the hydrogen always goes to the less substituted carbon, right, to generate the more substituted carbocation. So we put a hydrogen here, we have a plus charge here, and we also generated a Br minus in the process, right? But remember that this carbocation has a resonance structure. It's allylic. So if we actually, to accurately represent this carbocation, the way that we should draw it is like this. We have this resonance structure, or we can move the double bond over, and we have this resonance structure. So what we actually have is a resonance hybrid that has some positive charge here and some positive charge here. The way you can think about this, though, is that if the bromide ion attacks this positive charge, we get the 1,2 addition product. And if the bromide ion attacks this resonance structure, remember, I'm using this term very loosely because you can't attack a resonance structure, but to understand these kinds of reactions, it makes sense to look at them in this way. So now it would make sense that we would get the 1,4 addition product from attack on the positive charge here. So let me just ask you, before we go on to the next slide, which product do you think would be favored, right? We have what looks like a secondary carbocation and what looks like a primary carbocation. So you might think that this product would be favored. It turns out it depends on the reaction conditions, as we'll see. Okay, so at cold temperature, at low temperature, what we see is exactly what we would have expected on the last slide, right? twice as much of the 1,2 addition product is formed as a 1,4 addition product. What's strange, though, is that if we heat up the reaction, the 1,4 product predominates in the reaction mixture. So what is the explanation for that? Let's look at the potential energy diagram to understand this, right? So both of these products have the same first step. Both mechanisms have the same first step, which is attack of the double bond, protonation of the double bond to form a secondary carbocation. So that step is the same, right? But once we get here, those two reactions diverge, right? And it makes sense, like we said, since bromide is attacking the more stable secondary carbocation to lead to this product, the activation energy that leads to that product is smaller. So this product forms the fastest because it has a lower activation energy. So we call it the kinetic product. But notice that even though the activation energy that leads to the 1,4 product is higher, it forms more slowly. The product is more stable because it has a di-substituted alkene as opposed to a mono-substituted alkene. So since the product is more stable, this is referred to as the thermodynamic product. Because it's lower in energy. So if only we could get over this higher activation energy barrier, we could go down to this lower energy product. Or if we add enough energy, right, the 1,2 product can get back over the hump, and then we can jump over the larger potential energy barrier to get down to the 1,4 addition product. So if we go back one slide, what we could say is that we start out we form this carbocation, and then the fastest reaction is the bromide attacking to form the 1,2 product, right? But then this can leave, and so we can establish an equilibrium where every so often the bromide attacks the less substituted carbon, which gives us the more stable product, which is lower in energy. So this is the thermodynamic product. This would be the kinetic product. If we don't have enough energy to go back in this direction, then we're stuck here. If we do have enough energy to get back in this direction, eventually we'll funnel the product down to the thermodynamic product. As we see here, if we don't have enough energy to get back over this hump, then we'll stay stuck here because this forms the fastest. But if we do have enough energy, we'll go back and back over, and then we're good. Okay, so to summarize, conjugated, I want you to be able to see whether or not a compound is conjugated or not. This is going to be really important for a lot of chemical reactions that we're talking about. As we know now, conjugation leads to increased stability of compounds, and we can measure this by catalytic hydrogenation. We can rationalize the stability associated with conjugation using molecular orbital theory. The more p orbitals that we have stacked next to each other, the more we're spreading out electrons, the lower in energy that it is. And I want you to understand the mechanism for the hydrobromination of butadiene. It gives two products, and know what favors the kinetic product and what's going to favor the thermodynamic product.